Hey, hello guys. Today we are going to continue to talk about how to apply group theory to understand IR spectroscopy. So last time we talked about a very simple example, water molecule, right? So water molecule has, in terms OH stretch, we have a symmetric model, and also we have an asymmetric model. That's symmetry. So that's asymmetry. So that's an example we used last time. So actually, for IR spectroscopy, there's a lot of important applications for inorganic compounds. So today, so I'm going to show you example of metacarbonyl compound. Now, how can we use group theory to define the cell stretch for metacarbonyl compound? Okay. So shown here, okay. So that is a should be, sorry. Here should be a, there should be a trans. Okay, that should be a trans. Okay. That's a mistake here. It should be trans. Okay. It's a trans. And iron compound, iron carbonyl compound, and the diaminigand is a phenolphthalein. Okay, phenolphthalein. So let's say so. Go again. So it's going to be. Yeah, this phenolphthalein bidentate dinitrogen ligand. So then that first step is like we did before. Then what is the point group for this one? So then we can go ahead to how to deal with the two CO stretch here. So we have two CO stretch, right? So figure out how. So I think we follow the flow chart and define the point group. So just showing here. So that's a C2V. Okay, that's a C2V group. Okay, and I'm going to draw you where's the C2. So the dashed line is C2. Okay, that's a C2 rotation. Okay, then the sigma V. Okay, and you have sigma V and the sigma V prime. So the sigma V is going to be the plane contain the iron to iron carbonyl bond there. Okay, that's sigma V, and sigma V is perpendicular one. Okay, perpendicular. Okay, so then in terms of those two CO stretch, they are vectors, right? So we talk. Then what's a total representation? So we need to find out what's a total representation for two CO stretch. Okay, that's stretches. Okay. All right. So if you look here, so then E two CO then it don't move. We get 2. But for C2, what happened? But when you rotate it with C2, each CO move to another place to each other. Then we get 0, right? But for sigma V, so the sigma V contain these two CO, then that means they don't move, so we get 2. And if you get sigma V prime, they also exchange the position, and we get 0, right? So that's a total representation for this two CO stretch, right? That's pretty simple. Then we need to do, so that's first step. Then next step, what do we do? You need to do reduction step, right? So let's show you, make sure you know how to do reduction, okay? So here, so that's a reduction equation, okay, and so here is the answer. So we are going to have reduce them to get a A1 and a B1, two irreducible representations, okay. From here we can get a A1 B1. So you can follow this equation because that's a simple C2V point group. So the graph table is simple, and you can use this equation, or you can simply test the irreducible representation and here. So you can say what you can do is if you combine the A1 and B1, you will get this total representation. Simply 1 plus 1 you get 2, 1 plus minus 1 you get 0, 1 plus 1 you get 2, 1 plus minus 1 you get 0. So similar we did before, but make sure you can still use this equation to do the formal reduction, okay. And then we need to figure out whether not they are these A1 or B1, they are really IR active. So if we bring out the selection rule, right? So remember, so your ground state is always A1, and the excitation model is going to be either your A1 or the B1 we get it from here, okay? Then what's a tensor? Tensor means either that's a Z direction or X direction or Y direction, vibration energy, the infrared wave energy. So you can say for A1 you do get Z here, so okay, and for B1 you get X here, okay. That means they can both put them together, you can get a A1 non-zero product. So that means A1, B1, they are both IR active according to the selection rule. Okay, got it. Okay, so that's the selection rule. So we know they are IR active. Okay. And then you may wonder, what are actual, vibration model for A1 and B1, right? Last time when we talk about water, because that's simple. Actually, this molecule is also simple. We simply draw the symmetry, and in fact, the A1 in this case, so A1 model is iron. So actually, the same as water molecule. That's because they have, same point group. Okay, point group. So you get that's a, B1. That's asymmetry. That's a symmetry. So that's asymmetry. Okay. So that's similar as water, but also just give you a reminder, we can still use project operator to find out what's A1, how each individual cell stretch contribute to A1 model and B1 model. Okay, so for example, if we look at A1 model, say we can find out what's contribution. So for example, if you do A1, right, A1 here, if you deal with that, if you start with this cell stretch, like this one, and what you will see is, if you do E, it's going to stay there, right? So if you test this one first, if you do C2, what happened? This one will rotated to this position, and the first one E, you get let's just call this as CO1, okay, as CO stretch 1. So this one is with CO stretch 2, right? So what you get is, when you're under 1, you get CO1, and under C2, CO move to, the CO2, CO1 move to CO2, so you get a CO2. And here, what you get is no move, okay? This one, no move, is still the same. But when you go to sigma V prime, so you move to CO2. So overall, you get the A1 model equals to 2 CO1 plus, CO2. So that's this, we call that symmetry model. And if you do the same thing, you will get that you don't worry about the prefactor here. So you will get CO1 minus CO2, okay? So that's just not carbon dioxide, or just the substrate indicate different cell stretch, okay? So that's, you can use, use this projection operator to derive how each individual cell stretch contribute to the irreducible representations. So then you get A1 as symmetry and B1 as symmetric model, right? And the same principle as we deal with the how to construct MO orbitals. Okay, same idea. You do total representation, reduction, then we do projection. Okay, same idea. Okay. And then here is our experiment data. So you will see for this A1 and B1 stretch. So in fact, people, if you look at the publication, people will say, we have A1 stretch at what wave numbers and B1 stretch at which numbers. But anyway, so here is experimental IR data. Okay, IR data. So you can see it has two, strong cell stretch peak there. So one at 2077, another one at 2033. And I don't tell you which one is which, but think about how to assign them. Okay, which one is A1 and which one is B1. Think about how to assign. So think about the order molecule, okay? How we assign that, okay? Yeah, we can answer the question during the discussion section, okay? Yeah, make sure you know which one is which, okay? All right. All right, let's do another example. Okay, let's do another example. So here, so that's the cis iodide, tri-iron carbonyl, with the PME3 ligand trans to 1C. Okay, so this looks structure a little bit more complex than the first example, iron dicarbonyl. Okay, the same thing. You need the first step. You need to assign the point group. So what's a point group? Okay, right. So if you look at this molecule, the highest, you don't have rotation. Okay, no rotation. Okay. But you do get a, reflection. Plane, okay. So where the reduction plane, okay. But we do have one. So that's one. You contain this CO here. This CO iron phosphine, vector. And this just the screen plane, simply screen plane, okay? That's your reflection here. So, in fact, that's a CS group, okay? CS group. It's a very simple point group, Then we have, right now, we are dealing with 3 cell stretch, okay? 3 cell stretch. Then what's the total representation? No, next to that, we need to get total representation for 3 seal stretch. Okay, so make sure you know how to do that. Okay, so then I just show you the answer here. So you get 3 for E and 1 for OH. Then you do reduction rate. So you just need to do reduction. So use the equation or simply use the correct value for a prime and a dot prime. Then you can figure out that you are going to get 2 a prime plus 1 a dot prime for this total representation. So that's very easy. In fact, that's very easy. Okay. Then let's look at the what they are. Okay, in fact, they are all based on selection rule. They are all IR active because for 2a1 a prime you do get xy direction infrared wave energy, but for a dot prime you get z direction. So that means they are all IR active. Okay, that's simple. Okay, that's very simple. Okay, so then let's look at what are they. Okay, then you can do same thing. You can use a projection. Okay, right now probably it's better to do projection to figure out how each individual seal stretch contributed to the A1 to contribute to A1 a prime model and a double prime model. Okay, stretch mode. Okay, mode. Then I'm going to show you what are they. Okay, so the 1a1 a prime, sorry, right, it's going to be involve stretch here. Okay, no involve the just involve the this part. That's 1a a prime. The second a prime is, so you involve symmetry stretch here. Okay, symmetry stretch here. Then the a prime is going to be the asymmetry here, sym and asym. So here is only perpendicular. So here, so that's a part. Okay. Okay, you get that's a how individual cell stretch contributed to the irreducible A1 here, a prime, the second A prime, and the another a double prime. Okay, then let's look at what are the experiment data. Okay, that's where's the experiment data. Okay, let's see that. Okay, you can see here is the a stretch mode for a prime, second a prime, and the a double prime. Okay, then here is the experimental IR for these, for this compound. And you can see I also showed another similar compound, but you only replace a trimethylphosphine ligand with pyridine. Okay, but you will say what's the difference here? What's the same thing here? Information. But anyway, so let's look at the data for this trimethylphosphine iron tricarbonyl compound. So you have a stretch. You have one stretch at around also around maybe 20, let's say 2095. Okay, and you have second wave here around 2050, and you have third wave here for this one is about maybe 20. Let's just do 2023. Okay, let's do a good estimation. So per centimeter, and so if you compare the IR data for Pyridine derivative, so you see it has almost identical wave at higher wave numbers around here, but the third wave become shift to higher wave number compared to this one. So that's a difference. Okay. Then I give you a question here. So how do you assign each wave corresponding to first A prime, second A prime, and A dot prime, and say I compare these two spectra. Okay, so in fact, the example I show in this lecture, it's a inorganic chem paper. Maybe we published back to 2009 or 2010. So they are real. So those are real research data, and I was sending you guys the paper linkage. You guys can figure out what are they. Okay, and because I'm going to make a homework question beyond this, associated with this iron carbonyl compound. Okay, see you later at the Zoom discussion session. Okay, all right, so.